Okay, in this problem we're going to do a challenge problem, a problem mark 3. The problems marked 3 in your book are the more difficult ones, and it's involving the big three kinematics equations. So if you want to follow along in your book, page 40, 32. And in this case we have a person driving her car at 45 kilometers per hour, approaches an intersection just as the traffic light turns yellow. She knows that the yellow light lasts only 2 seconds before turning red, and she is 28 meters away from the near side of the intersection. Should she try to stop, or should she speed up to cross the intersection before the light turns red? The intersection is 15 meters wide, and her car's maximum deceleration is negative 5.8 meters per second squared, whereas it can accelerate from 45 to 65 kilometers per hour in 6 seconds. Ignore the length of her car and her reaction time. So this is a challenging problem. It's basically giving us two different problems that we need to solve and compare. It's giving us the problem is, can she stop before she reaches the intersection? That's problem 1. Or can she speed up and make it through the intersection, which is problem 2. So what we need to do is take the information, break it down into the individual problems, and then solve them both and compare in order to get our final answer. So I'm going to set the book aside, and let's start by following our guess steps. Let's zoom it out so we have some space to work with here. Okay, so let's look for givens. Let's look at if she stops, right? The information for if she stops or if she runs, right? If she runs through. All right, 30 meters and 15. I got to change this because in my book I have to swap out. I had an old edition book where this was number 30 and 30 meters. The numbers have changed a little in the newer edition, so let me go with the newer edition, which you guys should be looking at, which should have 28 meters and not 30. All right, so if she stops, we know her initial velocity is 45 kilometers per hour. We know that the yellow light lasts 2 seconds. So that gives her 2 seconds. Remember, it says ignore reaction time. So 2 seconds for her to stop. And we know that in order for her to stop in front of the intersection, she has to beat a delta x of 28 meters. And we know her maximum deceleration is negative 5.8 meters per second squared. So really, I can't use this number. This number is what I need to compare it to. What I know is how fast she's going, the time of stopping, and how fast she can, at what rate can she decelerate. That's the information I need to use. Then I have to compare it to this. Okay? I don't know that she can stop in 28 meters. I got to figure out if she can based on the specs of her car, and then use the 28 meters as a comparison. All right, well, what if she runs the light? Well, if she runs the light, we know that her initial velocity is still 45 kilometers per hour. We know that if she accelerates, she can reach 65 kilometers per hour in a time of 6 seconds. Okay, so somehow, and if she runs, she's got to beat a delta x of 28 plus 15, or 43 meters, right? She's got to run 43 meters through the light in order to clear it. So these are our two numbers we're going to compare to, basically. All right, let's figure out the first one, her stopping distance. So in this case, my unknown is delta x. Okay. And can I solve for her delta x in one step? So I know v naught, t, and a. So second equation will allow me to do that. So I'm going to set up second equation. Delta x is v naught t plus 1/2 a t squared. I'll solve in the same color. Delta x is. Now, v naught is 45 kilometers per hour. A is negative 5.8, t is 2. So can anyone see what the problem is? I have a problem. I can't just plug these numbers in, okay? And my problem is, like I've been telling you in the first few videos, you got to look at the units. Units must justify. And in this case, I got kilometers per hour for my speed, and I got seconds and meters per second for my time and my acceleration. Not going to work. Can't do it this way. You got to convert one of them so that they're all in like variables. So if I have a speed, not kilometers per hour, I need meters per second. So let's take the 45 kilometers per hour off to the side and let's convert that to meters per second. Always look at the units. Very, very, very important. Otherwise, you'll be guaranteed to get the wrong answer. So I'll do that down here. If I start with 45 kilometers per hour, and I want to go to meters per second. So I got to go kilometers to meters. So 1 kilometer, since this is on top, I put my multiple by 1. Okay, so 1,000 meters is 1 kilometer. And hours are on the bottom, so 1 hour is 3,600 seconds. This should be familiar to you from chemistry. You did similar things when you're simplifying things in chemistry. So hours cancel, I'm left with meters per second. So if I go 45 times, times 1,000 divided by 3,600, 12.5 meters per second. Now I know that I have 65 kilometers per hour in the second part, so I might as well do that now at the same time. So 1,000 meters per kilometer, 3,600 seconds per hour, kilometer, meters per second. So 65 times 1,000 divided by 3,600, 18.05, 5.056 meters per second. I don't need to round that down because I'm going to use that to solve a further problem. So don't round the early ones. Okay. Okay. So my V naught here. I'll go back to my first one. So I have 12.5 meters per second times 2.0 seconds plus 1/2 times negative 5.8 meter per second squared times 2.0 seconds squared. I have 4 seconds, meters, second squared, meters. So my units are good. 12.5 times 2, so I have 25 meters. And then 1/2 times negative 5.8 times 4 is a minus 1/2 times negative 5.8 times 4, minus 11.6 meters. So my delta x is 25 minus 11.6, 13.4 meters. Good. Looks good, right? So that means she can stop before she reaches the intersection. So that's working well for the stopping part. Now let's just do the run part just to make sure. Let's say she were to run. Can she run through the intersection? Because maybe she could do both, right? Maybe it doesn't matter. Maybe she has enough power to accelerate or she has enough breakage to stop. All right, let's slide over here. Again, my unknown is my delta x, right? Can she speed up at a point where she can get through the intersection? So let's go back to my equations. So I need to find delta x, but really what I don't have in the two delta x equations is a. I don't know a, but I know if she can go from v naught to v in a certain time, I can find a, and so this is a two-step problem. So in order to solve this, I'll write down my delta x equation that I want to use, right? V naught t plus 1/2 at squared, but then I'm going to use v equals v naught plus at. Solve for a first, plug it in here, and then solve for delta x. All right, so v, I'm going to get a by itself, subtract v naught over, so v minus v naught, and then divide by t equals a. Sorry I did a couple steps there in my head. Hopefully you can see what I did. So now I'm going to use my meters per second, right? 18.05, I know it's 5 bar, or minus 12.5 over 6 seconds, right? Because that's how many seconds it would take. So 18.05 minus 12.5 divided by 6. So the rate at which she can accelerate is 0.926 meters per second squared. This is meters per second up here. This is seconds. Meters per second is meters per second squared. All right, so I have my A. Now I'm going to use that, go back into my delta x equation. So delta x is, initial velocity is the same, 12.5. The time is 6 seconds, over which she, no, I'm sorry. Am I using 6? No, I got to go back to 2. I don't want to screw that up, right? Because 2 seconds is how long the light's yellow for. So I got to be careful there, right? So I really have 2 times, the time of acceleration and the time of the light, which is 2.0 seconds. I almost screwed up there using the wrong time. So this is where I tell you, it gets a little complicated when you have lots of things going on. Got to really pay close attention to what variables you're using in what situations. So there's my A. Now the time is 2.0 seconds squared. Second squared, meters per second, seconds, meters, right? So my units are going to cancel. So I have 12.5 times 2. Do that one in my head. And then 1/2 times 0.926 times 4. And that's a 5.556. So my final delta x here is a 30.6 meters. So what does that mean? Well, what that means is if she tries to run the light at 30.6 meters, she's going to end up right here, right, when it turns red, which is not good. It means she'll be running the red light and will create a danger for which she might get into an accident. So the final answer here is, what should she do, right? Should she stop? What does it say? Ignore the... Should she try to stop or should she try to speed up? That's the final thing. So the answer here, she should try to stop, and the justification is because she can stop in 13.4 meters, whereas if she accelerated, she would be stuck in the middle of the intersection when the light turned red.